So we'll talk about error correction today. So let's first talk about classical error correction before we go into the quantum. So let's say we have some bits to be transmitted, some information to be transmitted. Let's say that the bits are 0 or 1, and this information is to be transmitted over a classical channel. So the channel will introduce some errors in the transmission. So a 0 could be converted to a 1, or a 1 could be converted to a 0. So let's try to model this classical channel. So one model of this classical channel is what is known as a binary symmetric channel. So 0 has a probability, let's say P, of going to a 1. Similarly, a 1 being transmitted has a probability P of going to 0. And there is a probability 1 minus P of the bit being unaffected. So this is called a binary symmetric channel. So this is the model of the classical channel. Now, if we transmit information over this channel, then there is a probability P of an unrecoverable error. So probability P of an unrecoverable error. Now we would like to improve upon this and also see if there is a possibility of recovering the information completely, right? So the idea in classical error correction and in general quantum error correction also is to add some redundancy. So add redundancy. So what do we do? If I want to transmit a 0, I will transmit or encode a 0 as 0, 0, 0. So this will be adding two extra zeros, so adding some redundancy over here. And if I want to transmit a 1, then transmit 1, 1, 1. So in this case, we have encoded the logical 0 as physical 0, 0, 0, and the logical 1 as physical 1, 1, 1. Right? So now recovery in this case is possible if there is at most one error. So recovery is possible if there is at most one error. Well, if there is at most one error, then 0, 0, 0 could go to, well, if there is no error, then it goes to 0, 0, 0. If there is error on the first bit, it goes to 1, 0, 0. On the second bit, it goes to 0, 1, 0. And the third bit, it goes to 0, 0, 1. And if 1 was to be transmitted, so logical 0, logical 1, then if no errors, then we get to 1, 1, 1. If there is error on the first bit, then it is 0, 1, 1. Second bit, it is 1, 0, 1. And finally, third bit, it's 0, 1, 1, 0. Now notice that there is no intersection between these two sets. So these two sets that are there are no intersection. So at the receiving end, we could apply a simple recovery procedure or a rule that says that, okay, I can apply the majority rule. If there are more zeros received than there are ones, then decode it as a 0. If there are more ones received than there are zeros, then recover the transmitted bit as a 1. So apply majority rule to for perfect recovery. However, notice that if there are more than one errors, then these two sets could intersect, and then we cannot apply the perfect decoding procedure, right? Instead of the majority rule, we could also apply sort of parity check. For instance, we could check the parity means the parity is even if the bits are the same, it's odd if the bits are different. So we could apply a simple parity check on the first and the second, and the first and the third, right? So for example, if the the parity of the first and the second bit is different, and the first and the third bit is also different, that means that we know that the error has occurred on the first bit. If the parity of the first and the second is different and first and the third is the same, then we know that the error has occurred on the second bit, and so on. So we'll apply the parity check. So this is equivalent to apply parity check on bits 1 and 2 and 1 and 3, right? All right, so let's look at the circuit that we will build to do this error correction. So the circuit first consists of an encoding. So we have a bit over here. So the encoding circuit is one that encodes the 0 into a 000 and 1 into a 111. So this is the first. So let's say I have a bit B that is being transmitted. Then I can have a classical combination of classical C0 gate. So this is my first C0 gate. And then this is my second C0 gate. So B could be 0 or 1. So this first part is an encoding circuit. Right. So if I want to transmit B is 0, then I'll get the output over here as 000. If B is 1, then I'll get 111. Then the next is the channel that the bit goes through. So this is where the error can happen. So let me call this E. This is the classical channel. So this could be the binary symmetric channel, for instance. And then we have the next step is to have a detection procedure as to uh, what error has occurred, whether the first bit has been flipped or the second bit or the third bit. So the next step is to have a error detection procedure, or we call it the syndrome detection. So we'll call this error syndrome detection. So over here, we will, as I mentioned, we could do this via parity check. So let's do the parity checking of the first and the second and the first and the third. So over here, we'll use some extra ancilla bits over here. So let me have some ancilla bits. So 2 bits of ancilla. And then I have this so I'm going to do this. So this is a C0 gate. So these two C0 gates do the parity check on the first and the second qubit. So I'll start over here with a 0. So at the end of these, applying these two NOT gates, if the parity of the first and the second qubits, or not qubits, but bits, is the same, then we get a 0. If it's different, then we get a 1. So let's do the parity check also on the first and the third bits. So this will be the parity check on the first and the third bits. And now, once we have done the parity check, then we know what uh, type of error has occurred. So finally, the final step will be error recovery. So in this case, uh, the error syndrome detection would lead us to make some conclusions on which bit the error has occurred. So for instance, if the uh, parity of the first and the second bit is different, and the first and the third bit is different, then we know that the error has occurred on the first bit. So we will do the correction over here. So we'll apply this multi-control C0 gate. So this means that parity of the first and third is different, and this means that parity of the first and second is different. So that means that the error has occurred on the first bit, and so on. So we'll do the parity check over here, a recovery over here. So this is this will be on the second bit, and finally on the third bit. Right. So this is sort of a gate that gets applied, the C0 gate get applied if this bit is 0, whereas this is 1 where it gets applied if this bit is 1. Right. So this is the circuit that we would implement for the classical error correction. And finally, one wants to talk about what is the probability of an irrecoverable error. So recall that if we were to just transmit one bit instead of three, then probability of an error, if one bit was transmitted, is equal to P, right? So bit could be flipped with probability P. So probability of irrecoverable error is P. If we add the redundancy, what is this probability? So probability of variable error with 3 bits transmitted. So this is with the protocol of error correction. This will be if two errors or two or more error occurs, right? Because we can always correct the error if only one bit was flipped, but two errors or three errors occur. Right. So what is that probability? Well, there are three possible ways of two errors occurring. So 3C2, that is, and so this is equal to two errors would be P square into 1 minus P. So error occurring at any of the two bits and not occurring at one of the bits, or three errors. So this is three errors. So this will be if error occurs on all three bits. So this is 3p cube. So this is equal to 3p square minus 2p cube. And one can show quite easily that if p is less than half, then this is order of p square. Right. So provided we keep the individual bit flip error to less than half, then we have actually decreased the probability of an irrecoverable error from p to order p square. So that's classical error correction. In the next video, we'll look at quantum error correction.